sphere-to-sphere capacitance. There are two conducting spheres in the air, and our task is to calculate capacitance between the spheres. Sphere's diameter is 200 millimeters each, and the spacing between the centers of the spheres is 500 millimeters. There is an analytical solution, and we will verify our simulation results against it. The capacitance is the ratio of the charge to the potential difference, and I'm going to assign positive potential to one sphere and zero electric potential to another sphere, and then use QuickField to calculate electric field distribution and the charge values. So I will start QuickField now. In QuickField I create new problem. Problem name is sphere to sphere. Next. Problem type is Electrostatics and model class is three-dimensional extrusion. Okay. Here is the problem tree, and here is the geometry model editor window, and I will import the geometry model from the step file. Step file is used to exchange geometric objects between different CAD systems. Okay, so we have two bodies here. To distinguish one sphere from another, we can assign labels, and through labels we also provide physical properties. To assign a label to geometric object, we should select an object, and to select an object you should click it. So I click here, and the face is selected. Well, that would be a face of the grounded sphere, so I type here the name grounded. You see that the label appeared in the tree, and now I can select the geometric objects by clicking on its label. And I can assign physical properties to the label. Double click the label name and type in the potential value, which is 0 volts. Okay. Now let's assign the label to another sphere's face. I select the face, type in the label +1, double click the label name and specify the electric potential value, which is 1 volt. Okay. Remember, there is no electric field inside conductor, so there is no need to assign labels to conducting bodies and specify physical properties. But we should specify properties for the air surrounding these spheres. Our CAD model didn't contain the air, but we can add the air block here. Just click in empty space and enable the background region. You can change the dimensions of the region in percents. Let it be 300%. Background region is transparent now, but you can make any body transparent or opaque. Just right click and choose opaque. I click the face and the face is selected. To select the body you should click the selected face again, and the body which is behind this face will be selected. I will give the label A to this body. And for the air I specify electric permittivity of 1. Okay. Now the model and data are ready, and the last step before we can start the simulation is to build the finite element mesh. I will make the air block transparent again to see better what will happen when we build the mesh. You can build the mesh in 3 stages. First, the mesh is built on edges. Then the mesh is built on faces. And the last, the mesh is built in volumes. Now we can run the analysis. Yes, save all simulation files. Yes, open the results. And here are the results. It is the electric potential distribution along the air block surface. To look inside, you can hide the objects. Right click, hide. Now you see 2 spheres with electric potential plus 1 volt and 0 volt. Our task is to calculate the capacitance. We know the potential difference, we need to find the charge. And the electric charge belongs to the conductor's surface. To measure the charge, I can use the integral calculator tool. Click the sphere to select its surface, and here is the charge. Now if I divide the charge by the potential difference, I will get the capacitance value, which will be 1 picofarad. And the analytical solution gives us almost 7 picofarad. What is the reason for such large difference between calculated and analytical results, and how to amend this difference? The difference is caused by the poor mesh quality, and to amend the difference we should adjust the mesh. In most real problems the field distribution is non-uniform. QuickField utilizes the finite element mesh method to compute the field distribution. The space is divided into elements. Inside each element, the potential is considered to be linear. Let me show you. I will unhide all. I will use the cut by plane tool and switch to the 2-dimensional section window. And here you can see the field lines. In fact, these lines should be smooth curves, but we have line segments with sharp corners instead. That's because the finite elements are huge, and inside each element the potential distribution is considered to be linear. If we would have smaller elements, we can get better approximation to the smooth curves. This is geometry model again, and QuickField chooses finite element mesh sizes depending on the geometric object size. Large object, large element size. Small object, smaller element size. QuickField doesn't know in advance what will be the field distribution. So let's change the spacing to manual. I select, right click and drag to select everything, and switch the spacing to manual. 0.1, 10 centimeters. Well, and for the spheres, I will select only spheres. It will be 10 times smaller, 0.01, 1 centimeter. Now let's build the finite element mesh on faces in volumes and run the analysis again. Okay, let's take a look at the results. Again, I will hide the air block and will measure the electric charge. And now, if I divide the charge by the potential difference, I will get the capacitance, which is 6.07 picofarads. And the analytical solution is 6.99. The difference is 14%. If you need better accuracy, just build a denser mesh. Well, in this case we knew the analytical solution in advance, but what should we do if we do not know the analytical solution? Well, you should build the denser mesh anyway. Just in this case you will compare the intermediate results. For example, forget that we have analytical solution. We get some results and the capacitance is 6.07 picofards. How accurate is it? Let's build denser mesh. The mesh spacing was 0.1 in the A block, and I will set it to 0.05. And for the spheres I will set it to be 10 times smaller. Let's build the finite element mesh on edges, on faces, in the volumes, and run the analysis again. It took about 2 minutes to compute the results. Now let's take a look at the results. Again, I will hide the A block and select the sphere surface to compute the charge. 6.4. It was 6.07 on previous iteration. And if I divide 6.07 by 6.4, I will see that the difference between previous results and now calculated results is about 5%. You can repeat these steps till you get the desired accuracy. I will stop for now and demonstrate what else you can do with the results. I will unhide the A block. Well, to look inside you can use cut by plane tool. You can adjust the plane position and direction. You can hide the plane. You can adjust the field picture representation. You can see the two-dimensional picture in a separate window. Here you can build the contours. And get the field distribution along the contour on the XY plot. Or in the table. All the values and pictures you get here you can copy, or you can use the Windows built-in tool to copy pictures. You can also calculate the integrals. We have already seen how to calculate the electric charge stored on the surface, but you can also select the volumes and calculate integrals in the bodies. Remember, first click to select the face, second click to select the body beneath this face. And here is the stored energy. The capacitance is twice this value divided the potential difference squared, which is 7.12 picofards, and the analytical solution, as you remember, is 6.99 picofards. 7.12 divided by 6.99. The difference between calculated capacitance in QuickField and the analytical solution is only 2%. This is just another way to verify the accuracy of your results. You can use different approach to calculate the capacitance. In fact, this case could be simulated as a two-dimensional problem, and on our website you can find the video and the simulation files both for two-dimensional and for three-dimensional analysis.